Assalamualaikum. This is your Thermodynamics 2 class, and today is lecture number 20. So, can anyone confirm what's appearing on screen right now?
Said lecture 20, chapter 13.
Okay. Thank you so much. Okay, so in the previous lecture, we already see some of things related to gas mixture, which is chapter number 13. Okay, so first we will solve one problem related to chapter 13, which is gas mixture, and then we will move to chapter number 15. Okay, so first we have to read the statement. So a perfect gas mixture consists of 4 kg of N2 and 6 kg of CO2 at pressure of 4 bar and temperature of 25 degrees Celsius. So initial temperature and final temperature of a mixture is known to you. Okay. Also the pressure of the mixture is also known in the question. So you have to calculate the specific heat value CV at constant volume and pressure of the mixture. Okay, so there we have to note that we are talking about the mixture CV and CP, not the gas CP and CP. Okay. If the mixture is heated at constant volume to 50 degrees Celsius, okay, so T2, which is the final temperature, is mentioned, and it is also mentioned it is at constant volume. Okay, so this is an important point over there. And find the change in internal energy, change in enthalpy, and change in entropy of the mixture. Okay, so three things you have to find: internal energy, enthalpy, entropy, and also you have to find CV and CP value of the mixture. Okay, so you have to note on the question, and then we will move toward the solution. Okay, so before this, we have already know that it is a gas mixture and consists of two different gases, which is nitrogen and CO2. Okay, so as a starting point, we need the value of CP and CV for both of the individual gases as well. Okay, so for this you can go to table A2, okay, and find out the CP and CV value for these gases. Okay, so first thing will just write it down over there. So that CP value of N2, which is equal to 1.041 kilojoule per kg dot Kelvin, and similarly CV value of N2, which is equal to 0.745 kilojoule per kg dot Kelvin. Okay, so in a similar way, we also need the CP value and CV value of CO2. Okay, so CP value of CO2, which is equal to 0.842, and also the unit kilojoule per kg dot Kelvin, and CV value of CO2, which is equal to 0.653 kilojoule per kg dot Kelvin. Okay, so these values, after note down this value, we have to move towards the things which is already known to us. So first thing that is mentioned in the question is mass of the gas N2, which is 4 kg, and also we have the value of mass of CO2, which is equal to 6 kg. Mixture pressure is known to us, which is 4 bar. Initial temperature of the mixture is also known, which is 25 degrees Celsius. We will have to convert it into the Kelvin, equal to 298 Kelvin. And similarly, we have the value of final temperature of mixture, which is at constant volume, which is 50 plus 273 and times out to be 323 Kelvin. So these things we already know. So first thing we have to find is the CV mix and CP value of the mixture. Okay, so for this we can easily apply one relation, which you can see that mass of N2 for first gas and mass of CO2 If we multiply with this, you can say it will be CV mix, and if I can just open this equation, it turns out to be mass of N2 into CV of N2 and plus mass of CO2 and CV value of CO2. Okay, so this equation can be denoted by like this. Okay, so now in the equation we already have all the values. Okay, so CV value we have to find. So this is our required thing for the first part. Okay, so mass of N2 is known to us. CV N2 we can get from table A2. Mass of CO2 is also known to us. CV value of CO2 is also known to us from A2. Okay, so these values are also known to us. Okay, so just you have to put the value and solve it for CV mix. Okay, so CV mix will be equal to mass of N2, which is 4, CV value of N2, which is 0.745, plus mass of CO2, which is 6, and CV value of CO2, which is 0.659. Okay, and you have to divide the cumulative mass, which is this term. Okay, so this will be equal to 10. Okay, but 4 plus 6. Okay, so now if you can just solve it, you will get the CV value of the mixture, which is equal to 0.6898 kilojoule per kg dot cal. Okay, so this is the first thing which is required in the question. Now second thing is we have to find the CP value of the mixture. Okay, so just by using again this relation, you have to just replace CP with CV with CP for both of the sides. So here is CP of N2 and here it becomes CP of CO2. Okay, so we have to use again this equation and it turns out to be CP mix, which is equal to 4, and CP value of, now we have to use CP value of the mixture. So CP value of N2 1.041 and 6 into 0.84, the CP value of CO2. And if I can divide with the 10, it is the cumulative mass of the both of the gases, so it will be equal to 0.9216 kilojoule per kg dot cal. Okay, so now both of things which is required is known to us. Okay, so you have to note it down and move towards the next part. Okay, so now from the problem statement, we have to find the change in internal energy. So delta U is equal to mCV T final minus T initial. Okay, so this you can just denote that it is for the mixture. Okay, so CV value we have to use for the mixture. Okay, so which we already found in the previous slide. Mass value we have to use the cumulative mass of both of the gases because we are talking about the mixture. So final temperature of the mixture is known to us from the problem statement, 323 Kelvin, and T1 is also Ti is also known to us, which is the initial temperature of the mixture. Okay, so now we just have to put the values. So 4 plus 6. CV value of mixture from the previous slide is 0.6898, and temperature of the mixture is final temperature which is 323, and initial temperature of the mixture is 298. So if you can solve it, you will get the delta U value, which is 172.45 kilojoule. Okay, so this is the first thing which is required. Now another thing which is required is delta H to find the enthalpy. So as you already know that enthalpy is basically MCP delta T. Okay, so now we have to use MCP T final minus T initial, and again it is for mixture. So mass of the mixture, which is 4 plus 6. Cp value of mixture you can find the previous slide, 0.9216. Final temperature of mixture is 323 and initial temperature of mixture is 290. So if you can solve it, you will get the value of change in enthalpy, which is 230.4 kilojoule. In a similar way, the last thing which is required in the problem statement is change in entropy. Change in entropy, basically you have to use the equation which is Cv log of T, T2 or you can say T final over T initial plus gas constant log of T and Vf over V initial. Okay, and because it is not per unit mass, so you have to multiply mass also. Okay, so now here it is mentioned in the question that we are talking about that if the mixture is heated at constant volume. Okay, so it means that this term can be eliminated from this part. So now our equation only become m Cv log of E and Tf over Ti, and again it is for mixture. Okay, so now we just put the value inside this equation and we will get the required thing. 4 plus 6 Cv value of the mixture from the previous slide, which is 0.6898, and log of 323 is the final temperature and 298 which is the initial temperature. And if you can solve it, you will get the delta S value, which is 0.55557 kilojoule per Kelvin. Okay, so now this is the required last part. Okay, so now the solution is completed. If you have any question, you can ask me. You can note it down. Then we move towards the next part. Okay, so now moving towards chapter 15, which is the chemical reaction. Although these both chapters are interlinked with each other. So now we will come towards the chemical reaction specifically for the combustion processes. Okay, so the chemical reaction are the process during which the chemical composition of the component changes. You already know from the chemistry knowledge as well. Okay, so this means that when we are talking about chemical reaction, so either there is the production of heat energy, or either it will be the require of heat energy. Okay, so for produce heat energy we call as exothermic reaction. So in which the heat is required. Okay, so it is the endothermic reaction. Okay, so we already know from the chemistry knowledge as well. And combustion is one of the most important chemical reaction, particularly in study of thermodynamic system. And it is a chemical reaction during which a fuel is oxidized and a large quantity of energy is released. Okay, so we already know that whenever we have to use the combustion inside our combustion chamber for the IC engine or either in the steam power plants, okay, so we have to mix fuel with the air. Okay, so it means we have to provide source of oxidization to produce the combustion process, to initiate the combustion process. Okay, so however, it is not like this that we have to supply large amount of air, or it is also not feasible to supply less amount of air. So we have to supply some specific amount of air to produce the combustion process or to initiate the combustion process. If we do not supply the proper quantity, so it's mean our combustion cannot be initiated. Okay, so we will see later and discuss about it. Okay, so now while talking about the combustion, definitely the fuel is the important part. Okay, so the fuel basically any material that can be burned to release thermal energy is called fuel, and most familiar fuel which consists of hydrogen and carbon, and they are called hydrocarbons, and are denoted with CnHn. Okay, and hydrogen fuel exists in all phases like coal, gasoline, natural gas. Okay, so based on categorization, we have to categorize hydrocarbon into three forms. One is the solid hydrocarbons. So in solid hydrocarbon is basically we call as a coal. Coal is basically type of solid hydrocarbon. Coal also contain different amount of oxygen, hydrogen, sulfur, moisture, and ash. So it is difficult to give the exact mass analysis for coal since its composition vary considerably from one geographical area to the next. Okay, so this is the first classification. Second classification is liquid hydrocarbon. So liquid hydrocarbon, which most commonly we use in our IC engine as well. Okay, so in the IC engine or in the diesel engines, okay, so internal combustion engine we can use by burning these type of fuel inside the combustion chamber. Okay, so most liquid hydrocarbon fuels are a mixture of numerous hydrocarbons and are obtained by crude oil by distillation process. So we have to separate different hydrocarbons by using the distillation from the crude oil. Okay, so crude oil, and at the first stage of distillation, we get the gasoline, then kerosene, then diesel fuel, and then fuel oil. Okay, so these all depend upon what are the temperature at which the distillation takes place. So we will get the different type of gas fuels. So the most volatile hydrocarbon vaporize first, forming what is known as gasoline. The less volatile fuel obtained during the distillation are kerosene, diesel fuel, and fuel oil. The composition of particular fuel depends upon the source of the crude oil as well as the refinery. Although liquid hydrocarbon fuels are a mixture of many different hydrocarbons, but they are usually considered to be a single hydrocarbon for convenience. For example, gasoline is treated as octane C8H18, and the diesel fuel, which is we call as a dodecane C12H26. Although if we can say gasoline in the actual form, it is a combination of different type of gases. Okay, it is not just octane, but we can just for our convenience say it is octane. Okay, and similar for the diesel fuel as well. And the third form of the hydrocarbon is the gaseous fuel. So this gaseous fuel is also used in most of our combustion engines. Okay, so the gaseous hydrocarbon fuel, which is the natural gas, which is a mixture of methane and smaller amount of other gases, is often treated as a methane. The CH4 is the formula for the natural gas. Okay, so now here natural gas is produced from gas well, oil wells, which is rich in natural gas, and it is composed mainly of methane, but it is also contains small amount of ethane, propane, hydrogen, helium, carbon dioxide, nitrogen, hydrogen sulfate, and water. Okay, so you already know, I think that we have to use, nowadays we are using CNG and LNG type of gaseous fuel for IC engines as well. Okay, so basically on vehicle it is stored either in the gas phase at a pressure of 150 to 250 atm and recorded as a CNG, or in the liquid phase at minus 162 degrees Celsius, which is called liquefied natural gas. Okay, or we can say it is also, and then liquefied petroleum gas, which is also a byproduct of natural gas processing or the crude oil refining. It consists mainly of propane, plus LPG is usually referred as a propane. Okay, so these are the type of gaseous hydrocarbon which we use as a fuel in combustion processes. Okay, so this we already talked about what is your fuel and then hydrocarbon fuels. Okay, so this is table 15-9. So this table shows that your fuel and how much energy content they carries. Okay, because whenever we have to select the fuel which we have to use for the combustion process, so either we have to look for the energy content, and about the availability also is an important factor, but first important thing is the energy content. For example, if you want to produce high energy content, then you have to select that fuel which are producing high energy content per liter of the fuel. Okay, for example, if you can just notice that gasoline consists of 31,850 kilojoule per liter of the energy content. Okay, so this means that if we have to burn 1 liter of the fuel, it gives 31,850 kilojoule of energy. Similarly, if we can compare with the CNG, which is compressed natural gas, we get 8,080 kilojoule if we burn 1 liter of the CNG. Okay, so this is the criteria whenever you have to select the fuel in the combustion process, that how much energy it produce if we burn the 1 liter of the fuel. Okay, so this we already talked in the previous slide, that we have to we have to produce the oxidation process in order to initiate the combustion. Okay, so most commonly oxidizer we have to use and we have to mix with the fuel in the IC engine as well is the air. Okay, so what is the reason why we have to use air only? Okay, the reason is behind choosing the air is only because it is free of cost, available free of cost, and rest of the oxidizer are not available for the free. So that is the main reason behind that why we have to use the air as oxidizer. And 1 mole or a volume basis, dry air is composed of 20.9% O2, 78.1% of N2, 0.9% of argon, and small amount of CO2, helium, neon, and hydrogen. Okay, so this I am talking about the actual dry air. Okay, however, when we are analyzing the combustion process, specifically when we are solving some problem, so we can just say that dry air is approximately 21% O2 and 79% N2. So rest of the small amount of gases we just have to neglect. Okay, and the formula of air, you already know that this collectively we call as a air, which is 1 kilomole of O2 and plus 3.76 kilomole of N2. Okay, and together we can say 4.76 kilomole of air. Okay, so whenever we say in the problems that we have to use air, okay, so directly you have to know that we are talking about 1 kilomole of O2 and 3.76 kilomole of N2. So this is the standard thing. Okay, rest. Okay, so we already talked about this as a combustion. Okay, so now here in this slide it is mentioned that the fuel must be brought above its ignition temperature to start the combustion. So if you remember from the IC engines topic, that is the gas power cycle, that in the Otto cycle we have to initiate the combustion by using the spark plug, and in the diesel cycle we have to produce combustion by using by increasing the pressure inside the combustion chamber. Okay, so now here the main thing is that what we have to achieve in the combustion chamber is to make that the fuel must be brought above its ignition temperature. Okay, so this is the main reason we have to produce spark plug, or we have to compress the gases inside the combustion chamber to raise the temperature of the fuel above its ignition temperature so that it can start the combustion. If we cannot raise that temperature, the combustion cannot be started. Okay, so the minimum ignition temperature in atmospheric air are approximately 260 degrees Celsius for gasoline, 400 degrees Celsius for carbon, 580 degrees Celsius for hydrogen, 610 degrees Celsius for carbon monoxide, and 630 degrees Celsius for methane. Okay, so from this, if you can compare, you can easily judge that it is easy to initiate the combustion for the gasoline type of fuel rather than using the methane type of fuel. Okay, so these are the things which you have to consider while designing the combustion process as well. Okay, so now here the portion of the fuel and air must be in the proper range for the combustion to begin. So this I already told you that whenever we have to initiate the combustion, the portion of fuel and air must be in a proper range. So here it is mentioned that, for example, natural gas does not burn in air in concentration less than 5%, or also it cannot burn if the concentration greater than 15%. Okay, so we cannot choose the less percentage of air. We also cannot use the greater percentage of air. Okay, so we have to be in the specific limit for the combustion process. Then when we are talking about the reaction, okay, so we already know that at one side we have the reactant. So reactant is basically your fuel plus air. Okay, so in the combustion process, okay, and in the product we get some product as a result of the combustion process. Okay, so now here this figure show that a mass and number of atoms of each element is conserved during the chemical reaction. Okay, so that is basically which is shown over there is, okay, that I will explain in the next slide, which is easy to understand. Okay, so if you can see this equation, C plus O2, CO2. So what is the meaning that the mass is conserved during the chemical reaction? So it's mean that if we are in the reactant side, we have 12 kg of carbon and 32 kg of O2. So we get in the product 44 kg of the product. Okay, so it's mean that our mass is conserved during the chemical reaction. So this is the meaning of that statement. Okay, so now when we are using the combustion process, one important term we have to use is air fuel ratio. Okay, so air fuel ratio is basically decided by the manufacturer, or either you have to decide when you are designing the IC engine or you are designing the combustion process, what is the required amount of air and what is the required amount of fuel to produce the perfect combustion process or to initiate the combustion process. Okay, so basically air fuel ratio is the mass of air to the mass of the fuel. Okay, so you just have to divide these two terms and you will get the air fuel ratio. So for example, if in the combustion process you are using 1 kg of fuel and you are using 17 kg of air, so it means that air fuel ratio is 17 for that combustion process. Okay. So in order to provide the combustion, in order to initiate the combustion. Okay. So here if we can replace mass by number of mole of air and molar mass of air, and also we have to just replace number of mole of fuel and molar mass of fuel. Okay, so this is another term we can write in term of molar form. Okay, or we can say it is on a mole basis of the air fuel ratio. Okay, so this term we can also use for the problems. Okay, so similarly, the reciprocal of air fuel ratio we call as a fuel air ratio. So if sometime we have to calculate fuel air ratio, sometime we have to calculate air fuel ratio. Okay, so both terms have this difference. That one is the reciprocal of the air fuel ratio, which is the fuel air ratio. Okay, so coming towards one problem, so you have to read the statement, and this is 915-1 from your book. Okay, so you have to read first and then we'll try to solve. Okay, so this question defines that 1 kilomole of octane C8H18 is burned with air that contain 20 kilomole of O2, and figure is shown over there. Assuming the product contain only CO2, H2O, O2 and N2. So you have to determine the mole number of each gas in the product and air fuel ratio for this combustion process. So you have to note down the statement and then move towards the solution. Okay, so now this is basically a combustion process. So for all the combustion type of problems, we have to initiate by using the chemical reaction equation. Okay, so because this is not a chemistry course, so I will provide the chemical equation whenever this type of question you have seen in your final exam in the problem statement. Okay, so you do not need to remember the equation of the combustion process. Okay, so the combustion process from the data which is available is C8H18, which is our fuel, plus we have the air, and it is mentioned that we have to use 20 kilomole of air. I already told you air is basically mixture of 1 kilomole of O2 and plus 3.76 kilomole of N2. So this is our oxidizer, and it gives the reactant as X mole of CO2, and we also get Y mole of H2O and Z mole of O2, and we also get W mole of N2. Okay, so this is the chemical reaction for this type of combustion process. Okay, so first thing is to develop the combustion equation. We have to know these X, Y, Z, and W value. Okay, so then we can find the air-fuel ratio from this equation. Okay, so first you have to balance the equation. Okay, so I will start by balancing the carbon. Okay, so from, if you can see in the left hand side, so there is 8 carbons, and on the left hand side, right hand side, you will get the X number of carbon, and you can say X is equal to 8. Similarly for the hydrogen, on the left hand side you see the 18 hydrogen, and on the right side you can easily find there will be 2Y, because we are talking about monatomic hydrogen, and that turns out to be Y is equal to 8, Y is equal to 9. Okay, so similar process we have to apply the balance for the oxygen as well. For oxygen, there is 20 into 2 oxygen at the left hand side. So we are again talking about monatomic oxygen, which is equal to 2x plus y plus 2z at the right hand side. So we have the value of x and y with us. So just simply you have to put this value in this equation, and you will get the value of z, which is equal to 7.5. Similar process, you have to apply the balance for N2. Okay, so from here you can just say that 20 into 3.76, which is equal to W of, okay, and the right hand side is only W, so W becomes 75.2. Okay, so now we know the moles which are on the product side. So ZW, Y, and X. Okay, so you have to note down and move towards the next part. So by knowing this x, y, and z and w, we get the combustion equation as C8H18 plus 20 O2 plus 3.76 N2, and in the product side we get the 8 CO2, because we already find the value of x, and then y, the value is 9 H2O, and then the value of z, which is 7.5 O2, and also there will be the value of W, which is 75.2 N. Okay, so now this is the combustion equation by which we have to find the air fuel ratio. Okay, so for air fuel ratio, you already know air fuel ratio basically the mass of air over mass of fuel. Okay, so here we can say that mass is equal to N into M, and we can say it to be air, and number of mole into molar mass, and also we can say it will be for fuel. Okay, so now if you can see on the left hand side, the air consists of 4.76 mole. Okay, so we can, and also we have to multiply 20. Okay, so this is the value for the air. So n value basically it is 20 into 4.76, and molar mass of air, you just have to go to table A1, and you will easily find if you cannot remember it, and its value is 29 kilogram per kilomole. Okay, so similarly in the fuel, okay, so for fuel we have two components, C and H2. Okay, so these are the two fuel which make C8 HAT. Okay, so first we can just say that the number of mole of carbon. So number of mole of carbon, and here we are talking about the fuel. Okay, so we have 8 into 12, which is the molar mass of the carbon, and also we have 9 kilomole of H2, and from here we can say it will be 2, okay, which is the H2 molar mass. Okay, so if we can just divide these two things, you will get the air fuel ratio, which is 24.2 kilogram air and per kg of fuel. Okay, so this is how you have to find the air fuel ratio from the combustion process. Now the solution is completed. If you have any question, you can ask me, and then we will move towards the next part.
सर लास्ट स्लाइड दिखाइएगा एक बार।
Last catch is slide कौन?
सर लास्ट स्लाइड, सेकंड लास्ट, जो इससे पहले वाली स्लाइड।
अच्छा, वो तो सोल्यूशन था।
सोल्यूशन से देख लेना, नहीं होगा चले कोई नहीं, दोबारा देख लेंगे।
हाँ, काइंडली आप दोबारा उसको करना, मैंने उसको
कोई बात नहीं सर, दोबारा
जी जी please. Okay, it is a simple process. You just have to go through it. I think it is mentioned in the example 15-1. If you have book, you can easily find out. Okay, so now for your practice, what you have to do is you have to replace this 20 kilomole by 40 kilomole, and you have to repeat this question by yourself, and again you will get 0.2 absolute marks, and that would be the part of your assignment number 4. Okay, so and you will get I think you can send it to me by tonight, or either you can send it to me by tomorrow. Okay, so if you have any question, you can ask me, you can note it down, and then we will just stop at this point.